I have the pleasure to introduce Venkitesh. We'll be talking about covering symmetric subsets of the Boolean hypercube with affine hyperplanes.
Thank you. The topic is a slight variant of the classical hyperplane covering problem considered by Alon and Fioretti. So let me just start from there. And before we go ahead, just a note that we are working over the reals, not over finite reals. Characteristic 0 is the setting we are interested in. So what's the hyperplane covering problem considered by Alon and Fioretti? So their main theorem states that any family of hyperplanes that covers the Boolean hypercube. So this is the n-dimensional Boolean hypercube, 0, 1 to the n, covers all vertices of the Boolean hypercube except one point. In this case, we can choose it to be the origin, but it could be any other point. All the vertices except one fixed point. Then the family must contain at least n hyperplanes. So this was their result. And this was probably the first hyperplane covering problem that was considered. It was a question raised by Barani from a paper of Combiat, and Alon and Fioretti gave a nice polynomial based argument to give us this result, and this bound is tight. So you do have a configuration of n hyperplanes which covers all the points except the origin. So this is a tight bound. And in this talk, we will consider two extensions of this problem to what I call symmetric subsets. There have been numerous extensions and variants considered over time, including two very interesting results last year. In this talk, I'll present my attempt at a different extension. So let me just mention the few recent results. So Clifton and Huang gave us a multiplicity version of this problem. So the question here is cover all points of the hypercube except the origin k times. Okay, so you have a family of hyperplanes, and covering k times means every point must belong to at least k of the hyperplanes in the family. So cover every point except the origin k times and do not cover the origin at all. So this is the multiplicity version. And they gave tight bounds of n plus 1 when the multiplicity is 2 and n plus 3 when the multiplicity is 3. But from 4 onwards, they only have a lower bound of n plus k plus 1, and we don't know if it's tight. In fact, the configurations that we can construct are quite far away from n plus k plus 1, so there is a gap that we do not understand. And a little while later, Sauerman and Wigderson considered a polynomial version of this problem, where you do not insist on having a hyperplane arrangement covering the points, but instead you just take a polynomial. And now the question is, what is the smallest degree polynomial that can cover the vertices as per the same conditions? And for the polynomial version, they gave us a tight bound of n plus 2k minus 3 for all multiplicities greater than or equal to 2. Another variant of this question was considered by Aronson and a few others, and they call it the exact hyperplane covering problem, which goes as follows. Take a small subset of the hypercube, and the question is you need to cover the complement of this small subset using hyperplanes and not cover any point in this chosen subset. So for a fixed subset, cover the complement of S and do not cover any point in S using hyperplanes. And again, the same question, what's the minimum number of hyperplanes that you require? They gave tight bounds whenever this subset to be excluded has size at most 4. And in general, they have asymptotic bounds. So these are the two very interesting results that popped up last year. And this year, I'll give you some extensions. So some basics, what's the Boolean hypercube? It's just 0, 1 to the n. A slight notation, box n is the set of the first n positive integers. For any element in the hypercube, we define the Hamming weight to be the number of ones in that vector. And this gives you a nice gradation of the hypercube. You can partition the hypercube on the basis of the Hamming weights. The Hamming weight of vectors in the hypercube vary from 0 to n. So for each Hamming weight, you have a layer. A subset is defined to be symmetric if under permutations by coordinates, you are still within the same subset. So take any element, permute its coordinates, and you're still within the subset. This is just a definition, but a more nicer way to characterize these symmetric subsets is the following. Every symmetric subset can be put in 1-to-n correspondence with a subset of 0 to n. So on one hand, you have a subset of the hypercube which is symmetric. On the other hand, you have a subset of 0 to n, which is essentially the set of weights corresponding to the points in S. That's it. So we will introduce this additional notation. E lower bar is the collection of all points whose weights lie in E, Hamming weights lie in E. Okay. And for the rest of the talk, since we are only concerned with symmetric subsets, we will identify E with E bar. So this is the diagrammatic representation. The hypercube can be thought of as a layers partition according to the Hamming weights, and the representation in terms of subsets of 0 to n is on the right hand side. So you have taken layers corresponding to weights 6, 7, 8, 12, and 15. On the right hand side, they are just points 6, 7, 8, 12, and 15. Right? So what are our questions? So we start with a symmetric subset E, and we'll consider two extensions of the hyperplane covering problem. So one is what I call a non-trivial hyperplane cover. What does that mean? Well, you want to have a family of hyperplanes which covers the symmetric subset E, every point in the symmetric subset E, but does not cover the full hypercube, leaves out at least one point. So in this case, this red point is the generic point that is left out. The layers in E are here in orange, and the green indicates that they are being covered by the hyperplanes. Okay. So any cover that satisfies this property is called a non-trivial hyperplane cover. The second variant is a stricter condition, which I call a proper hyperplane cover, which means the hyperplane family should cover every layer in S, every layer in E, but among all the layers that are in the complement of E, at least one point should be left out from each layer. Right? So from the complement of E, no layer should be contained fully inside this cover. At least one point should be left out. So that's a proper hyperplane cover. And now we ask the same question. So once again, I've just worded the definitions here. So let me just go to the question. The question is, once again, what is the minimum number of hyperplanes that we require to cover in this way? Right. So HCN of E will denote the smallest size of a non-trivial hyperplane cover, and PHCN will be the smallest size of a proper hyperplane cover. Right. So how do we solve this problem? So let me declare, we solve this problem fully in this talk. So how do we do that? We do that by introducing what are called finite degree hyperplane closures. And what is it? Well, it's just a variant of the usual Zariski closure kind of object. So we just start with Hn, which is a set of all polynomials which correspond to hyperplane arrangements, by which I mean all polynomials which are products of linear factors. Okay, so any polynomial that's a product of linear factor, if you take its zero set, it will be a union of hyperplanes. That's what I mean. So only collect those polynomials which correspond to hyperplane arrangements, and let me call that Hn of S. So for a subset S, Hn of S is the set of all these hyperplane polynomials, so to speak, that vanish on S. And little hd of S is all those with degree at most d. So a polynomial representing a hyperplane arrangement with degree at most d exactly corresponds to a hyperplane arrangement with at most d hyperplanes. Right. And the degree d hyperplane closure of a subset is defined to be the common zero set of these polynomials. So one quick observation, which I'll state without proof, is that when you start with a symmetric subset and you look at the degree d hyperplane closure, the closure is also a symmetric subset. So we'll just do away with the set representation and just work with the weights in the rest of the talk. So let's start with a symmetric subset, and for a family of hyperplanes that covers E, Z of H denotes the common zero set. This is the set of all points covered by the hyperplanes. And then the closure essentially can be represented as the intersection over all hyperplane families that cover E with at most D hyperplanes. And the intersection is taken over the common zero sets. Okay, so this is the common region that is contained in any hyperplane arrangement with at most D hyperplanes that covers E. That's another way of looking at it. And yeah, that's it. So what do we have? So this is the description for the hyperplane closure, and this is just a recall for the definitions. So in terms of the hyperplane closure, we already have a characterization for the quantities that we require. HCN of E is exactly the minimum D, such that the degree D hyperplane closure is not full, because the fact that the closure is not full exactly corresponds to saying that there exists a hyperplane arrangement with at most D hyperplanes covering E but not the full hypercube. Right. Similarly, PHCN of E will be exactly minimum D, such that the degree D hyperplane closure is itself because no other layer is contained fully. Right. So where are we? So before we do anything, the main takeaway from this talk, if you do not follow anything else, should be this. For any degree D and for any symmetric subset E, the hyperplane closure corresponding to degree D for E will have a certain structure. It will be E along with certain initial layers and certain final layers. Okay, so the degree D closure will always look like 0 to A, union E, union B to N for some A and B. Now, each of these initial or final segments could be empty, which is why A could take the value -1 and B could take the value n plus 1. That's all. Okay. In particular, the closure could be itself for some choices of the degree where A is -1 and B is n plus 1. Okay. But in general, the structure is this for any subset. And we will make use of this. So, how do we arrive at this? So, I don't have time to give you the proof, but let me just take you through the outline. So I start with something called a closure builder lemma. So we are going to progressively build the closure and see that it has this structure. So if you start with a symmetric subset which has size at least D plus 1, and let's say A is the minimum of E and B is the maximum of E, then the builder lemma says that everything less than the minimum and everything greater than the maximum must be in the closure. Okay. So here itself we have sort of a first evidence towards the structure of the closure that we could have. Right? An initial segment and a final segment get into the closure. And what do we do with this? So the proof is a fairly easy, very neat consequence of the classical Alon-Furedi theorem itself. So it's a nice exercise. So I'm not getting into the proof, but why are we interested in this? So the significance is as follows. This is the important component of the whole argument that we're concerned with. So if you list down the elements of E as T1 to Ts, and suppose E has size at least D plus 1, consider the operator LD of E, which is just, if you look at the union is indexed over all D plus 1 subsets of E, and you're essentially applying the above lemma to each of those subsets and taking the union. So every subset that is inside this union must belong to the closure according to the lemma before. And you're just collecting all of them. So LD of E must be contained in the closure. And a succinct way of writing it down is this. So if E is listed down like this, then LD of E is just 0 to Ts minus T with E and TD plus 1 to 1. But this is not all. These layers are in the closure, but we need to repeat this. And that's the thing. So the set operator LD is defined like this. So for sets of size at least D plus 1, it's this. At most D, we don't really do anything. So it's just E itself. But now we are interested in repeatedly applying this operator. So LD bar of E corresponds to repeated application. You just add all the layers that you keep getting by applying this operator again and again. Finally, somewhere this operation should stabilize. And the main theorem is that this is the hyperplane closure. You keep adding layers by using this lemma. Wherever the process terminates, whatever you have at that stage, that is equal to the hyperplane closure for degree D. And this is true for any degree and for any subset. Okay. So this is the main theorem about hyperplane closures. What does it say about the covering problems?
Try to finish up soon, but I think you're on track.
Yeah. Okay. I think I have a minute or so. Yeah. Okay. So once we have this, we have immediately the characterization for the hyperplane covering numbers in terms of LD bar, which is the same thing. But then you can do a bit more, a little bit of simplification can be done. So let me just define for every I between 0 to n, a subset Ti, which is 0 to I minus 1 union n minus I plus 1 to n, just a union of one initial and one final segment. In particular, T0 is the empty set. We will allow for that as well. And the condition that LD bar is not equal to the full set to 0 to n is exactly this. There is some I between 0 to D, says that E union Ti is not full, and size of E minus Ti is at most E minus I. The condition that LD bar of E is equal to E exactly says that T of mod E minus D is contained in E. Okay. So what's the final solution once we have this? So using this simplification and whatever characterization we have, the final solution to the problem is that for any proper symmetric subset, we need proper because we are looking for hyperplane covers that avoid at least one point of the hypercube. Any proper symmetric subset, the non-trivial hyperplane covering number HCM is the minimum D such that there is some I satisfying these properties. E union Ti is not full, size of E minus Ti is at D minus I. And the proper hyperplane covering number is exactly mod E minus the max I such that Ti is contained in E. So just to finish up, what does this say about the first problem that we considered, Lon and Furedi's problem? Well, it just says that if you take the symmetric subset 1 to n, excluding the origin, then the hyperplane covering number and the proper hyperplane covering number are both the same and they are equal to n, because since we are excluding only one point, non-trivial cover and proper covers, both notions coincide. So the Alon-Furedi statement is a special case of both of these. And that's the talk. So thank you.
Okay, let's all thank the speaker. Unmute yourself and clap or clap react. So there's a question in the chat from Galen, which is, do you know anything about the either matroid structure or orientation matroid structure of this hyperplane arrangement? For example, if two hyperplane arrangements both cover your set, what properties do they have in common? I could also like to ask this question.
Oh, right. So, yeah, right. So there is some sort of an underlying matrix structure, but I'm still not clear about it. I think we did discuss about it some time ago, and I still have to figure out what exactly there is. But over time, I'm more and more convinced that there is some connection with matroids. But I don't think it would be of an oriented sort, however. I think it would be the usual matroid structure. But yes, for the second thing, if we have two hyperplane arrangements, well, all you can say is that the intersection of their covering regions covers the symmetric set that you have. That's the only thing you can say for sure. And there could be more additional layers that get covered in the intersection, but they may or may not be in the closure because the closure has to account for every possible hyperplane cover. So the only thing that you can say for sure is that take any two distinct hyperplane covers, their intersection contains a given symmetric set. I don't think anything more can be said.
Is there people like think about sets that have other kinds of symmetry? For instance, like symmetry under like, I want to say like reorientation, but like switching zeros and ones in some coordinates.
Oh,
Like
yeah,
kind of like other
that's
kind of
right.
symmetry you can have. Or people like thought
That's
about
right.
covering sets like that.
Yeah. So that is quite immediate, although I didn't mention here. So uh, since we're concerned with polynomials with a total degree bound, right? This vector space of polynomials with a total degree bound is affine invariant. You can always do an invertible affine transform and you'll get the same family of polynomials. So you can take any invertible affine transformation of the Euclidean space which maps the hypercube to itself, and the closures will get mapped to the closures. It's just that the orientations of the layers will change, but the closure results will still remain the same.
Okay, so I think
Yeah.
we should probably try to move to the next speaker.
Yeah, sure. So I'll stop sharing. Thanks.